Okay, so let's do an example using total energy head and finding pressures and velocities along horizontal streamlines. Now this, I believe, is called a Pitot tube, and what they're used for, they're these small tubes put underground with manometer fluid here, and they're used to measure pressures and velocities of the streamline. So these streamlines can be caused by a variety of things. Maybe in this case there's a airplane moving this way, a really big airplane, and it's causing the air around it to move, and we want to find out the velocity of these streamlines or the fluid. So we can go ahead and call this, let's call this point 0. We'll call that point 0, and we want to find the velocity of point 0, okay? Notice here, this manometer fluid is mercury, and we'll call gamma of this air outside just gamma sub F, okay? So, the very first thing you want to notice that all of this is in static equilibrium. The air inside this pitot tube and this manometer fluid, all the way up to this point here, there it's completely static. It's not moving. The velocity inside this tube is 0. That's what's causing this mercury to stay the way it is right now. And there's a height difference here of h. Okay. So we know how to work with static pressures. We just take a path, and the net change of that path is going to be equal to 0. If we start at 0, we go through the tube, come up here, go up here, and we end back at 0. So we know that the change in pressure is going to be equal to 0, right? So let's start our path. We'll begin here at point 0. And we'll go this way, and this way, and this way, and this way, and we'll hit the pitot tube right here. And notice here, we said the velocity in this tube of air is 0. So this point right here is actually called a stagnation point. I just write stag. And all a stagnation point is where the velocity is equal to 0. So at that point, because the fluid in here is in static equilibrium, the velocity here is 0. Okay, so we'll keep going. We'll keep going down this tube. We're going to go down, 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 until we hit this point. Okay, here we change from air to mercury. Okay, so we keep going. We're in mercury now. Okay, and we come up here, and here we change from mercury to air. Okay, we keep going and we keep going, and just to be careful, let's just put another point here. We could have just gone all the way up, but let's put another point here, representing that we are going from underground to above ground. So here we're at ground equals 0. And we'll come along here, we'll keep going up. Here, let's change direction. Let's go this way. Let's go this way, and then here let's change directions again, going up. Okay, now we're back at point 0. So the total pressure change along this green path we drew is going to be equal to 0. So let's name these paths. We can do that in maybe blue. We'll call this path path 1. Okay, from point 0 to the stagnation point. That's path 1. Okay, path 2 is from the stagnation point down into this tube up to this point. Okay, we'll call this path path 3, right, from this point through the fluid, through the mercury up to this point. That's path 3. We'll call this path path 4, from the mercury here to the ground level here. we call this point, or this path, 5, from the ground to some point here where we started to change directions. And this short path right here we'll call path 6. And then back up here we'll call path 7. Okay? So we have path 1, path 2, path 3, path 4, path 5, path 6, path 7. Okay? Let's define a few more dimensions. This distance here, we'll call it y3. Okay? It's path 4. And then we'll define this distance as y2. This is from the ground level to where we change directions here, so this point. And then up to that stagnation point we'll call y1. Okay, from this distance up to point 0 or path 1, that's y1. Remember, we said the total change in pressure is going to be equal to 0 along this entire path. So let's write that down. The change in pressure is equal to the change in pressure of path 1 plus the change in pressure of path 2 plus the change in pressure of path 3 plus the change in pressure of path 4 plus the change in pressure of path 5 plus the change in pressure of path 6 plus the change in pressure of path 7. All of this is going to be equal to 0. So change in pressure of path 1. What's that? Well, we know how to calculate pressure using the static pressure equation, but here we're not changing height, we're just changing horizontal distances. So for now, let's call this a question mark. Path 2, from the stagnation point down here, well, we can use static pressure. Negative gamma, in this case, air, so we'll call that gamma F, times the change in height. Actually, this should be positive because it's a negative and we're going down, so that's two negatives. Let's make a positive. That's y1 plus y2 plus y3 plus h. Right? That's the pressure from here all the way down to here. So that's y1 plus y2 plus y3 plus h up to this point. Okay, so that's positive. That's a pressure change. That's a positive pressure change. How about 3? Path 3, this path. So it looks like we're going up, so it's going to be negative gamma of mercury times height. Change in pressure of path 4. Path 4, remember, is from here to here. And that's negative gamma of fluid times y3, right? Because that's in air, and that's the height of y3. Change in pressure of path 5 would be negative gamma F times y2, right? Here's 5, where we're going up, it's negative. This is y2, a distance of y2. Change in pressure of path 6. Here we're changing horizontal distances. We don't know how to calculate that yet, so we'll just keep that question mark. Okay, so change in pressure of path 7. That would be negative gamma of fluid times y1, right? We're going up, so it's going to be negative. And you know, when you go up, the pressure decreases, so that's why it's negative, and it's a distance of y1. Okay? And we'll continue this example in the next video.